We have evaluated the constraints on small signal Y parameters in order to maximize the gain of a 2-port amplifier. Now, let us get some more intuition behind it. It is quite simple as it turns out. For this, we will use the circuit equivalent of the 2-port of the small signal 2-port. We know that the circuit equivalent of the small signal 2-port consists of a conductance Y11, a control source Y12 V2, another control source Y21 V1, and a conductance Y22, okay, where this voltage is V1 and this voltage is V2, and these are of course the port currents I1 and I2. This circuit is what corresponds to the Y parameter description of a 2-port network. And to this we add a source Vs and its source resistance is Rs or source conductance is Gs. And we have a load resistance RL, okay, or a load conductance of GL. Now, first of all, Y21 is the forward parameter, that is, it takes V1 and drives a current into port 2, okay. So, Y21 transfers signal in that direction, and Y12 in the opposite direction, it takes V2 and draws current into port 1, okay. So, that is Y12, that is the reverse parameter. Now, we already said that we would like the reverse parameter to be 0 in order to avoid instability, okay. Now, it turns out it is possible with some combinations of source and load impedances and the correct value of feedback parameter, there could be instability. But if you have this reverse to be 0, then there is no such possibility, okay, that we saw from the expression. So, we want Y12 equal to 0 . For unconditional stability, we have not rigorously defined the stability here, okay, and we won't do it, but essentially from our expression we don't want the gain going to infinity, okay, which means instability or output without an input, okay. So, once Y12 is 0, we can simply remove this control source. So, all we are left with is a voltage divider on this side and effectively a current divider on this side, okay. Remember, the 2-port, it responds to this V1, and here we see that V1 is Vs divided by this resistive divider. Now, what does it mean to have Y11 equal to 0? It means the input is open circuited, and this means no voltage division, okay. That is, if this resistance is infinite, Y11 by the way is conductance. So, if it is 0, this resistance is infinite. So, all of this Vs appears across port 1, okay, and that is the common sense thing to do anyway, because if you have a resistive divider, you will get something less than the source voltage. Now, you want to get all of the source voltage here, okay. And similarly, Y21, this control source produces some current depending on the value of V1. Now, that current, a part of it goes into Y22 and a part of it goes into RL. So, there is current division. So, to avoid this current division, to make all of this go into the load, which is what you want, right, because you are not interested in what goes into this. You want to maximize the current that goes into this, consequently the power that is delivered to RL. So, you want all of this current to go into that one. So, this should also be an open circuit, that is Y22 must be 0. Okay. Y22 is 0. So, we again have an open circuit looking into port 2. Okay. So, which means there is no current division. When I say no current division, this is between Y22 and RL. Okay. So, that is all that is there to it. That is what these constraints mean. You want all of the source voltage to appear across port 1 and you want all of the current from the control source Y21 V1 to go into the load. So, that is a very simple intuitive explanation of these constraints. And finally, we wanted Y21 to be as large as possible, and that is obvious. That is in fact the gain. That is how much the two port responds to the voltage on port 1. Okay. If you go on increasing Y21, more and more current will be pumped into RL and you will maximize the power gain. Okay. We wrote the expression for the gain and found the constraints, and the constraints are not some mysterious stuff. So, there is a very obvious explanation for it, and this is it. Okay.